A very important consideration about the overall performance of the network is how efficient the network is. In this module, we are going to address this aspect. First, we are going to look at a formal definition of it. Then, we'd look at the factors which play a key role in affecting the efficiency. We would also compare and contrast throughput versus efficiency, and we'd reach at an expression of average accuracy, average efficiency. Let's look at the boiling water analogy. Boiling water analogy is a classical way to describe a system in which water is put in pot and it is being boiled. There are certain factors, for example, the flame, the pot, the angle at which the burner tries to heat up the pot, the overall material, the alloy being used in the pot, its width, and its overall makeup are going to determine how soon this water would get boiled. Do you remember? We talked about boiling water in Murray and boiling water at sea level in Karachi are two different things. So efficiency is actually the effort that it takes to reach certain level of performance, namely throughput. The overall effort is quantified in terms of resources that it takes, time it consumes, and the overall complexity of the system that is determined in the design level. The factors which affect efficiency include the access protocols, because generally we have seen that more is the number of users, and if the users are getting successful transmissions across, it's a highly efficient system. So when we compare collision-based versus contention-free protocols at the access layer, we realize that Ethernet is not very efficient at high collision rates. Using larger frames is a good way to have lesser overall redundancy in terms of header, but using larger frames on shared links is going to be problematic. So we use large frames on singular WAN links. Another factor that affects efficiency is the overall serialization, or in other words, conversion time from being parallel to being serial. Now, when we look at the serialization delay on WANs, it tends to be unfair for short frames because when the long frames get serialized, they choke or disrupt the serialization process of short frames. Let's look at this figure. Here we see that short frames are less efficient, of course, because each frame comes with its own header, and large frames are very efficient. But on shared links, these large frames are going to have a devastating effect on the performance of certain users which have shorter frames. Leonard Kleinrock, one of the founding fathers of the modern day internet and the deviser or inventor of the local area network GARD, wrote a beautiful paper titled Creating a Mathematical Theory of Computer Networks. This is excerpted from his PhD thesis work. In this work, he presented a relationship between throughput and efficiency. Although we would establish, intuitively speaking, a linear relationship between throughput and efficiency. But his experiments and his findings were quite interesting, which gave us slightly tweaked kind of interpretation. Here we see 3 clusters. From the top, it is shown that the response time is improving, the throughput is increasing, and the efficiency is improving. With improved response time means the overall time is being curtailed. So you see that the particular group of plots that this particular section is referring to is actually the response time increase, you see here, these group of curves, that the response time is getting improved from 1 to 2 to 3 to 4 to 10. So the throughput would also increase and the efficiency is going to improve. But if we keep the response time constant here, we see that for a constant response time, when the throughput increases, the efficiency of course improves, reaching up to 100%. In another case, we see here that for the same efficiency, if the response time improves, the throughput also increases. So the interplay of throughput, efficiency with respect to the response time gives interesting insight. So we can see that if we scale up the capacity slower than the throughput, while keeping the average response time constant, the channel efficiency is going to increase, reaching up to even 100%. Another paper titled Efficient Behavior of Small World Networks gives an expression for the average efficiency of a network G. Here we see that this average efficiency is a function of the nodes in the network and the distances between these nodes. So larger the distance is going to have an adverse effect on the average efficiency, and shorter distances would increase the efficiency.